Hi, this is podcast 13B. So on your syllabus, you won't see 13B. That's because I forgot to put it on there. 13 was supposed to include this material. I forgot it. This is a relatively short podcast, but important, and it will be included on your first exam. So the first test is on Friday. It's same format as last year's test. There's an example of last year's test posted under test keys on Brightspace. Same format, but not the same test. So don't study that test. I always write a new test. It'll cover podcast number 1 through 13B. So this one is included. It'll be at Friday, 10:45 till noon. You're going to use the lockdown browser. So you did that practice test last week, and that will count toward your grade for this test. And don't forget, you also have to do that group recitation this week. So just this podcast and the test this week and the recitation. So we've been talking about the cytoskeleton, and one important aspect of the cytoskeleton is it can be used to move vesicles and organelles around with motor proteins. So this is a freeze etch micrograph where the material is frozen and then digested away, leaving just these fibers, and these fibers are part of the cytoskeleton. And here's a microtubule with a big vesicle on it, and then these may be actin filaments or intermediate filaments or both, but these motor proteins attach themselves to vesicles and actually move them, and it's pretty fascinating if you haven't seen these things work before. There's a bunch of them. So there are dyneins. These are individual genes that code for different proteins that are related to each other, called dyneins. They move toward the minus end of microtubules. And kinesins, there's a whole bunch of different kinds of them. They move toward the plus end of microtubules. And then there's microfilament associated motors, which are types of myosin. And this is more what you're familiar with if you're familiar with how muscle cells work. Kinesins have this sort of shape where they have these feet domain, and we'll see this in an animation, and then a connection, and then a cargo binding domain. So this is where they grab whatever they're going to move, and these are the things that actually bind to the microtubules and walk. Dyneins are more like a wheel sort of shape. They move by rotating this wheel and then unrotating that wheel. And then myosins have a sort of like a hinge domain, and we'll talk more about those at the end of the class. So from a microtubule organizing center, MTOC, which might be a centriole, could be a centrosome, or neither of those, a basal body, for example. There will be microtubules that have their minus end originating at the microtubule organizing center, and then plus end away from the microtubule organizing center, in this case, on the periphery of the cell. Kinesins always walk toward the plus end, dyneins always walk toward the minus end. I'm going to show you this video now, give you another link to another video, which is just, you can see on the side of this video that we're going to watch. It's a little bit goofier, but it's really good and worth your time, but I'm not going to go over it in this podcast. So here is an animation of a kinesin molecule walking on a microtubule. There's a microtubule. There are the foot domains, and there's the kinesin molecule dragging this large vesicle. So there's would be the cargo attachment domains. Here are the foot domains. You can see one swings in front of the other ones. We're going to go over that in detail. And they're able to pull with a decent amount of force on these big vesicles. Okay, and then this is the one that I want you to watch for extra for fun. Although I'm not going to test you on it, it's just like I said, it's worth your 5 minutes to take a look at it. Okay, so as we just saw on that animation, you have the foot domains, the stalk of the kinesin molecule, and then a cargo domain that binds to the cargo. And you can actually bind lots of different things to these. So in an experimental system, a lot of times they bind a fluorescent bead to these kinesin molecules so they can watch it move. And they are walking toward the plus end of the microtubule, the end of net addition, and away from the minus end. And they use ATP in walking. So the cycle of walking, if we say this is the lagging foot and this is the leading foot, okay? So the leading foot binds ATP. That causes conformational change. That causes the lagging foot, the one behind, to swing forward, okay? This was in behind and now is in front, okay? When that swings forward, the now lagging strand, which was originally the leading strand, leading foot, splits ATP, and then the cycle starts over again. So again, we have the foot in front and the foot in the back. The foot in front binds ATP. That causes a conformational change. That causes this foot in the back to swing forward and become now the front foot. Now the foot that is now in the back but was in the front splits that ATP into ADP plus P, and the now leading front foot gets rid of its ADP, and you start the cycle over again. Okay. You can, with these motor molecules, you can do some physics in that you can actually measure the force on which they're pulling on these motor molecules. You can do this with laser light trap. So you take something that is going to capture light, like a bead that's going to capture light, and you focus a laser on that bead, and because the dual nature of light in that it acts both like a particle and like a wave, you can exert physical force on that bead by shining a laser on it. So you have a laser on this side and a laser on this side holding a, say in this case it's an actin filament because they're using myosin as a motor molecule to measure strength, but you could also do kinesin and have this be microtubules. But the motor molecule is going to pull on this bead, and you can measure the force at which it's pulling by how much laser energy you have to exert in order to keep this bead from not moving. So you can get an idea of how many newtons, for example, is an individual motor molecule exerting on its substrate, and then calculate up, how if we know, for example, myosin would be in muscle, how much force a whole muscle can exert, a whole muscle cell. Then you can back calculate and get an idea of how many interactions between myosin molecules and actin filaments are happening. But getting back to kinesins and dyneins on microtubules, a lot of the information that we get from these in order to figure out how these molecules work comes from AFM, which stands for Atomic Force Microscopy. We have one of these instruments on campus. They essentially work like a old-fashioned record player. So you have a very, very fine probe that gets dragged over the surface, and this surface is going to have 3 dimensions to it. As it gets dragged over the surface, these probes get deflected up or down, and then deflection up or down is recorded and drawn in a computer screen so you can get an idea of the shape of things. So here's an actin filament with myosin on it, and AFM pictures of that. We also saw an AFM picture before when we were looking at lipid rafts in a membrane. Here is a scanning electron microscope picture of cilia in mammalian tracheal cells, like the lining of your throat. These things are constantly beating in one direction, moving mucus and things that are trapped in mucus up to your throat, and then you cough it out. These are the cells that can be damaged by smoking or vaping, for example. So you have less of an ability to clear things from your trachea. These are powered by microtubule movement, and so motor molecules, kinesins and dyneins on microtubules, as is the tail of a sperm cell. The sperm cell moves great distances in order to achieve its function in fertilizing an egg. If it were human size, it would be swimming the equivalent of Maine to the United Kingdom across the Atlantic Ocean. And as we said before, all the mitochondria are in the neck area here near the head of the sperm, which does not fuse with the egg, and therefore you don't, in almost all cases, you don't have mitochondria from the father contributed to the mother, so all your mitochondria came from your mother. Up until this summer, actually, most of the ideas of how we thought sperm moved was much like this, that it would, the tail would snake back and forth, sort of like watching an eel swim. But some new imaging techniques showed that that's not true, that sperm actually moves more like a corkscrew through the water. So I'm going to watch this little video to see that. Okay, isn't that cool? All right. In a sperm tail, you have at the base of the sperm a basal body leading to an axoneme, and the basal body is got a microtubule structure, and the axoneme has a different microtubule structure. So the basal body has triplets, the axoneme has doublets. There are motor molecules in between these microtubules. And what is happening is the motor molecules are walking on adjacent microtubules, but those microtubules are fixed at their root. And so it's as if this whole structure was something like a pole vault pole that was stuck in the ground, and a monkey or a small human would be walking up that pole vault pole, exerting force on it, on one side of it, and causing it to bend in one direction. And then that gets released and monkeys walk up the other side, and it causes it to bend in another direction. And of course, that model may be adjusted now that we think that sperm are actually only beating in one direction. But the motor molecules walking on fixed microtubules are the things that are causing the beating that you can see in those videos. This structure that you see in an axoneme above the basal body that gives rise to this structure, it has a 9 pair plus 2, 1, 2, 3, 4, 5, 6, 7, 8, 9 plus 2, if this structure moves, like in a sperm tail. And if it doesn't move, there is no central 2. It's a 9 plus 0. Here's a H5P question for you. Okay, so if we look at this more closely, there are diene molecules that are walking toward the minus end of these microtubules, and they are connected to another set of microtubules, not only by the diene, but by another protein called nexin. And these diene molecules are walking, causing what would be sliding motion because they are both stuck in the basal body at the base, because they are trying to slide past each other and it can't. It causes a bending instead. So they're walking toward the minus end. Here's the plus end, and it causes their neighbors to bend over like that. But if you destroy these cross links by this nexin molecule, you don't get any bending. So they have to be connected to each other to get this bending. Otherwise, they would just slide past each other. There is a condition you probably hear about if you go to medical school, or if you watch Grey's Anatomy, or any of those med shows, called situs inversus totalis, where all the organs left-right asymmetry is switched. So typically you would find the heart on the left side of the chest, but in people with this mutation, it's found on the right side of the chest. It's a mirror reversal, and it's thought to be that it may be caused in a mutant form of diene. That during the developmental process, you have a diene that is causing movement in the wrong direction, and that sets up developmental chemical gradients that are in the wrong direction, and everything has a mirror reversal. And often, people don't know until they get an exam where they can't find heartbeat until they go to the other side. Here is an example of where in normal cilium you see these diene arms between the doublets of the microtubules in the axoneme, and those are missing in some of the mutants. We've been talking about motor molecules in this podcast, and mostly motor molecules that walk on microtubules like diene and kinesin. Myosin is another type of motor molecule that walks on actin, which are microfilaments, and we will talk more about that in detail at the end of the class when we talk about specialized cells. That's it.